Good morning, children. Today we will discuss about ABCD matrices, cavity stability criteria for confocal resonators. ABCD matrices, cavity stability criteria for confocal resonators. Let us go with the presentation. Okay, ABCD matrices, cavity stability criteria for confocal resonators. Let us see. What is a confocal resonator? So it is a type of optical resonator. So confocal resonator, which is a type of optical resonator which uses two facing spherical mirror. So here in the case of confocal resonator, we will use two facing spherical mirror whose focal lengths are same. That means here we have to consider two spherical mirrors and which those two focal lengths are same. That means two mirrors focal lengths are same and foci also should be coincide. The focal length of a spherical mirror is 1/2 of the radius of curvature. F is equals to half r. So here F is a focal length and r is the radius of curvature. R is equals to 2f. Let us see resonator. So ABCD matrices, or we can say ABCD matrices or ray matrices. So the aim of these ray matrices or ABCD matrices is wave looping. What is wave looping? Runs continuously. Wave looping is nothing but it runs continuously. So the stability criteria for confocal resonators, let us see here. So here we obtain the condition to be satisfied by R and D. So that resonator is stable. So when the resonator is stable, when the condition should be satisfied by R. So R is here radius of curvature and D is nothing but distance between two mirrors. So stability criteria. What is the meaning of stability criteria? Stable condition. Stable condition. Let us see the confocal resonator. So this is a pictorial representation. So this is one mirror M1. This is mirror M2. This is focus center. And this is the axis. So this is confocal resonator. Now, stable resonator. So in this case, ray of light keep bouncing back to the two mirrors. So how the resonator is stable here? The ray of light keep bouncing back to the two mirrors and it should be identified because of the periodic focus is provided by spherical mirrors. So here what is the action of these spherical mirrors? The periodic focus is provided by these spherical mirrors so that it is identified by these mirrors. That means whenever the rays keep bouncing back to the two mirrors, so that process is identified by these spherical mirrors. Now, unstable resonator. So, what will happen here in the case of stable resonator? Rays of light keep bouncing back to the two mirrors. Here, unstable. In this case, after a few of rays from this process, the ray escape from the resonator. So, whenever the rays escape from the resonator is said to be unstable. Now, let us consider a cavity. So, cavity it is made up of two mirrors and consider a cavity which is composed of two mirrors of equal curvature R and focal length F. So, which is separated by a distance t on the axis. So, we obtain the matrices which represents the propagation of rays through a homogeneous medium and the reflection of the ray from the concave mirror as the following terms. So here we can see now we will obtain the matrices which represents the propagation of the rays through a homogeneous medium, not an inhomogeneous medium. Here the propagation of rays through homogeneous medium, reflection of a ray from the concave mirror. Now let us see the translation. So let us consider a propagation of a homogeneous medium. That means here we have to consider a homogeneous medium and the ray is propagation of a homogeneous medium in which planes? XZ planes. Here we have to consider X plane, Z plane. So the ray is propagation of a homogeneous medium in the XZ plane. It is described by its height x and the angle it makes with the optical axis is z-axis. So we consider rays only traveling near the axis and only the makes small angles with it, which is called paraxial approximation. Let us see. So here this is the diagram. So here this is x1, x2. So here we are considering here x-axis, z-axis. So here we have to consider x and z direction. So the ray is propagating in the homogeneous medium in x and z directions. So here this is x1, this is x2, this is AP, this is CQ, and here we have the triangle ABC, and here we have the angle theta. So here AC, which is D, AC is equals to D. AP, which is equals to x1, AP equals to x1. So here this is the line represents Z1, and this is the line represents Z1 plus D. So here x-axis, z-axis. So here x dash is nothing, which is equals to, so here we can observe tan theta. So BC by BC by AC, which is equals to tan theta. So BC by AC is nothing but D here. AC is D. BC by D is equals to tan theta, or BC equals to here d tan theta. Tan theta is nothing but here x1 dash. X1 dash. So change here x1 dash. Tan theta is nothing but here x1 dash. So CQ, which is equals to AP. CQ equals to AP, which is equals to x1. So x1 dash here it is slope, which is tan theta. So BC by AC is nothing but here tan theta. So let us see it here. So that x and theta are small. So here x and theta are small. Sin theta equals to tan theta. So which is equals to theta. So let x1 and x1 dash is equals to dx by dz be the position and the slope of the ray at a plane z equals to z1. So x1 is the position. Here x1 is the position, and x1 dash, which is slope of the ray at a plane z equals to z1, this plane. So here we wish to find the position and slope of the ray z equals to z1 plus t in the same medium. So here we have considered here homogeneous medium, and here x1 dash are the position. x1 is the position of the ray, x1 dash is slope of the ray at a plane z equals to z1, this plane. Now we wish to find the position and slope of the ray z equals to z1 plus t, the same medium. Since slope in the above terms is same, x2 dash is equals to dx by dz. So x2, change in x2 is x2 dash is equals to dx by dz at z1 plus t, because we are finding here at z1 plus t, which is equals to dx by dz at z1, which is equals to x dash. So x dash is equals to dx by dz. Okay, that is x2 dash is equals to x1 dash. x2 is equals to here x2 is equals to bq. x2 equals to here bq, which is what is bq? bq is nothing but here bc plus cq. So bq equals to bc plus cq. So what is bc here? bc is equals to, and bc equals to, let us see, cq is equals to ap. cq equals to ap. So here cq is ap. bc already we have find out here. bc equals to dx dash or AC tan theta. BC equals to AC tan theta. BC equals to AC tan theta plus AP. X2 is equals to x1 dash d plus x1. Or x2 equals to x1 plus x1 dash d. So thus we represent the initial ray by the column matrix. Here we will represent initial ray by column matrix. So from equation number 1 and 2, what is equation number 1? So from equation 1, x2 dash equals to x1 dash. This is equation number 2, and here x2 equals to x1 plus x1 dash d. Equation number 2, x2 equals to x1 plus x1 dash d. So from these two equations, we can represent a initial ray by the column matrix. So x2 x1 dash equals to 1 d 0 1 x1 x1 dash. So T is equals to 1D 0 1, which is the matrix of translation. So det T is equals to 1. Now already we have seen the translation. Now let us see B reflection. So let x1 and x dash be the coordinates of a ray before suffering reflection from a mirror of radius of curvature C. So before reflection, x1 and x1 dash be the coordinates of a particular ray. So before the reflection. So let us see it here. So this is the mirror, and here this is incident ray, and this is reflected ray. This is reflected ray. PB is the reflected ray. AP is the incident ray. So here's the x and z axis here. So the distance from here to A, which is U, distance from origin to B, it is V. So reflection of ray from a concave mirror. So this is a concave mirror. Let x2 and x2 dash be the coordinates of a ray after collision. So here before collision we have different coordinates, after collision we have different coordinates, collision coordinates. So reflection makes the position coordinate to remain the same. So x2 equals to x1. So slope of internal ray is x1 dash, which is equals to x1 by u. Similarly for second ray, x2 dash minus x2 by v. So here, so this is slope of the internal ray is x1 dash equals to x1 by u. For second ray, x2 dash, which is equals to minus x2 by a. So this is incident ray, and this is reflection. So for the reflection, we will consider here negative sign. So we know that 1 by x equals to 1 by u plus 1 by eb, which is equals to 2 by r. So here 1 by r plus 1 by r is equals to 2 by r, where u and v represent object and image distances from the mirror respectively. So here u and v are object distance and image distances from the mirror respectively. So a positive value of r corresponds to the concave mirror. Negative value of r corresponds to the convex mirror. We always measure the slope of the ray with respect to the forward direction of travel. So we always measure slope of the ray with respect to forward direction of a travel. Thus, slope of the initial ray would be x1 dash, which is equals to x1 by u from figure first figure. So where x1 is the height of the ray of the mirror. Similarly, slope of the reflected ray would be x2 dash, which is equals to x1 by v. So let us consider x1 dash minus x2 dash, difference between slopes. So these are the difference between slopes. x1 dash minus x2 dash, which is equals to x1 by u plus x1 by v. Since x1 dash is equals to x1 by u, x2 dash is equals to minus x1 by v. So x1, let us take the common as x1, 1 by u plus 1 by v. So x1 dash minus x2 dash, which is equals to x1, 1 by u plus 1 by v, which is equals to, so here 2 by r. 1 by u plus 1 by v is equals to 2 by r. So x1 dash minus x2 dash is equals to 2x1 by r. x2 dash is equals to x1 dash minus 2x1 by r. So let us consider x2 dash here. This is equation number 3. So from equation 1 and 3, we may write the matrix x2, x2 dash, 1, 0, minus 2 by r, 1, x1, x1 dash. Therefore, r is equals to reflection 1, 0, minus 2 by r, 1, which is a matrix reflection. So that r is equals to 1. So we obtain the ray coordinate after any number of reflections and traverses by simply multiplying the matrix together. So here we obtain the ray coordinate after any number of reflections and traversals by simply multiplying the matrix together. So here what is the meaning of traversals? Translations. So system matrix S can be written as bracket, square bracket, reflections, translations, or traverses, reflections, traverses. So we get, so by multiplying these reflections and traversals, we'll obtain a ray coordinate. So here system matrix, which is equals to multiplication of reflections and traversals. So we get S is equals to ABCD. That S is equals to AD minus BC, which is equals to 1. So here, as the resonance is stable, if even after any number of passes, the ray should remain close to the axis. That means here, whenever the resonance is stable, after any number of passes, the ray should remain close to the axis. So, okay, if we impose this condition stability criteria as follows. That means here, if we consider this is the condition as the stability criteria, let us see it here. So x naught, x naught 1 dash, x1 by x1 dash, xn dash. So this is the condition. So here, let us see the diagram. Here the ray is passing from A to B. So here these two are the mirrors, M1, M2, and this is the silver shaded region. This is also silver shaded region. This is R1, R2. Inside this one, it is the reflecting surface. This is the reflecting surface inside. So the distance from here to here it is d by 2, and distance from here to here it is d, and this is AB. So here the ray starting from line A to B, from this to here, A to B to M1, again from M1 to this M2, again from M2 to M1. That means here we can observe a circular trip and returns to AB. Again if it comes to AB, 0. That means a ray starting from AB to M1, M1 to M2, again M2 to M1, again M1 to A. Circular trip which is AB equals to 0. Solution of exist from the equation x2 by x2, x2 dash, which is equals to lambda x1, x1 dash. This is equation number 4. So this is the solution of exist from the equation. For such a solution, ray would be diverges for lambda greater than 1. Since that x2 greater than x1, theta 2 is greater than theta 1, which produces diverging ray, which can be shown in the figure. So by the definition, x2 dash is equals to a, b, c, d, x1, x1 dash. This is equation number 5. From equations 4 and 5, if you consider characteristic eigenvalue equation, a minus lambda is equals to 0. That means a is abcd minus lambda, I means 1, 0, 0, 1. So abcd minus lambda into multiplication lambda 0, 0, lambda. So a minus, here we have the minus, so a minus lambda, c, b, d minus lambda. So if you consider characteristic eigenvalue equation, a minus lambda equals to 0. That means this is the equation into x1 dash, which is equals to 0. So this is characteristic eigenvalue equation that will be satisfied by the equation. Now a minus lambda, c, b, d minus lambda equals to 0. So if you see it here, a minus lambda, d minus lambda minus bc equals to 0. Since ad minus bc, we are applying the condition ad minus bc equals to 0. So if we multiply, we will obtain ad minus a lambda minus d lambda plus lambda square minus bc equals to 0. Lambda square minus lambda, by taking lambda common here, a plus d plus ad minus bc equals to 0. But ad minus bc is equals to 1. Ad minus bc equals to 1. So lambda square minus lambda a plus d plus 1. Ad minus bc 1 equals to 0. The solutions of the above equation are, so lambda 2, lambda 1. So these are the solutions for this above equation. A plus d by 2 minus a plus d by 2 whole square minus 1 whole power minus 1 by 2. Lambda 1 equals to a plus d by 2 plus a plus d by 2 whole square minus 1 whole power 1 by 2. By using this condition, bc plus or minus root of b square minus 4ac by 2a. Now, these are the two eigenvalues of the system matrix S. So, if you write cos theta equals to a plus d by 2, so lambda 1 can be written as cos theta plus I sin theta, which is equals to e power I theta. So, lambda 2 equals to cos theta minus I sin theta equals to e power minus I theta. Already we know cos square theta plus 1 equals to sin theta. So, theta must be real, and hence a plus d by 2 lies between minus 1 and plus 1. So A, B, C, D, which is equals to, this is the equation which we have with reference to the BSc second year matrix algebra in optics first chapter. We have taken these matrix. So this is the matrix which was taken from the BSc second year matrix algebra in optics first chapter. And ABCD equals to 1 minus d by R1 minus 3d by R2 plus 2d square by R1 R2 minus 2 by R1 minus 2 by R2 minus 4d by R1 R2 minus d by 2 minus d square by 2 R1 plus 1 minus d by R2 3d by 2 minus d square by R1 minus d by R1 plus 1 minus d by R2 1 minus 2d by R1. So by solving, A equals to 1 minus d by R1 minus 3d by R2 plus 2d square by R1 R2. So D is 1 minus 3d by R1 minus d by R2 plus 2d square by R1 R2. So by multiplying, we will obtain this one. So substitute these equation in equation number 6. So if you substitute A and D values in equation number 6, we will obtain this one. This is the obtained equation. And here if we solve this one, so here we have minus 1 less than or equals to 1 minus d by R1 minus 3d by R2 plus 2d square by R1 R2 plus 1 minus 3d by R1 minus d by R2 plus 2d square by R1 R2 by 2 less than or equals to 1. So here we have to know. So by solving here, since a plus d by 2 equals to dividing with 2, we will obtain. So this is A, this is D. So by solving, substituting A and D values, A plus D by 2, we will obtain this one. So adding plus 1 on both sides, we will obtain. So this is the required equation. And plus 1 minus 1 gets 0. Here it is 2. So we will obtain the same equation here. So 0 less than or equals to 2 into 1 minus. So here we are taking 2 as common. And here we are taking 2d by R2 as common. So we will obtain this required equation. 0 less than or equals to 2 into 1 minus d by R1 minus 2d by R2. 1 minus d by R1 less than or equals to 2. And 0 less than or equals to 1 minus d by R1, 2 minus 2d by R2 less than or equals to 2. 0 less than or equals to 1 minus d by R1 into here taking as 2 common, 1 minus d by R2 less than or equals to 2. Cancellation 2 throughout this entire equation will obtain 0 by 2 less than or equals to 1 minus d by R1, 1 minus d by R2 less than or equals to 2 by 2. By solving 0 less than or equals to 1 minus d by R1, 1 minus d by R2 less than or equals to 1. So let G1 is this one, G2 is this one. So for a stable resonator R1 and R2 and D must be satisfied this condition. Now we will introduce two parameters. So G1, G2. So here what are R1 and R2? Radius of curvature of first mirror, radius of curvature of second mirror. Let us see it here. So G1, G2 lies between 0 and 1. This is equation number 7. So this condition can be expressed in terms of a stability diagram as shown in the figure. So this expression we can represent in the diagram. So for the clear regions of equation number 7, it is not satisfied and G1, G2 is greater than 1, then cavity is stable. So the three conditions can be expressed as the reason in the diagram. R1 equals to R2 equals to D by 2, R1 equals to R2 equals to D, R1 equals to R2 equals to infinity. So these are the three conditions in the diagram. So this is the stability diagram. So here we have mirrors concentric. These are the confocal mirrors. These are planar mirrors here. And this is x-axis and this is y-axis here. Now see. These are the confocal resonators. G1 equals to 1 minus d by R1, and here this is here we can observe the planar here, a point, and here this is here we can observe this confocal in the diagram. It represents here. So concentric here we can see. So G2 equals to 1 minus d by R2, and this is the stability diagram. So the three conditions can be expressed. R1 equals to R2 equals to D by 2, R1 equals to R2 equals to D, so which is confocal. Here this is confocal, this is the condition. R1 equals to R2 equals to infinity, plane parallel. So here this is the infinity, and concentric, symmetric concentric, it is D by 2. So here R infinity it is distance, G1 equals to 1 minus D by R1, G2 equals to 1 minus D by R2, R1 and R2 are the radii of the curvatures. So this is the stability criteria for the confocal resonators. Thank you, children.